My name is Borys. I'm our senior scientist at PBS Biotech, and my poster here today introduces our newest vertical wheel in the family, the MiniPRO bioreactor. So my history is I've worked in the field of developing processes for scale up of pluripotent stem cell aggregates for about the last 10 years. And in designing and optimizing and testing these protocols and scale up, a lot of it has been focused traditionally on hydrodynamics and how we can scale up what we optimize in our mini systems, our PBS 0.5, into the large scale. And we've really mastered that in terms of being able to tune the agitation rate to maintain our aggregate sizes throughout scale up. But as we've moved farther from pluripotent stem cell expansion, one thing that we really noticed is in these large scale reactors, our CDO clients come to us and they often say, okay, we need a process in the 3-liter, 15-liter, 80-liter to differentiate down this lineages. And our first question is often, what is your gassing strategy? What oxygen, what pH do you want to control it at? And always the answer that we get is, I don't know. So we have to decide in each one of these different stages what the optimum recipes are for controlling those key parameters. And that's really challenging to do at these larger scales. So one of the main points of our MiniPRO system is to have that controllability and that recipe building at the small scale. So the MiniPRO is actually 4 parallel bioreactors at the 500 ml scale. And it's built with the end users, aka the scientists, us in mind. So it has some really neat features, including each vessel has a built-in perfusion cap. So it's a retention filter for large particle perfusion. And it's got all the tubing set up to use with individual pumps on each reactor for your perfusion systems. Each one has built-in sensor spots to control our oxygen and pH. So like I said, I'm very familiar with hydrodynamics and optimizing that environment. In these smaller systems, there's not a lot of room to add a bunch of probes in it. And that's a disadvantage when we're trying to control our oxygen and pH. So the sensors on the side allow us to do that without impacting any of our hydrodynamics. It's also got ports on the front to allow for all closed system sampling, which is very convenient. And then other scalability to our 3-liter. So my poster is kind of broken up into 2 main experiments, or it's broken up into 2 main case studies. On the right hand, or on our left hand side, is describing why the MiniPRO is advantageous over our traditional PBS 0.5, which is run in the incubator. And on the right hand side is describing how the MiniPRO truly is a better scale down model for our 3-liter and above. So when we look at our bioreactor and we compare it to the traditional PBS 0.5, we knew that the 0.5 was a wonderful scale down model in terms of its hydrodynamics and being able to replicate either microcarrier cultures or PSC aggregate cultures. But what we started to notice was that cell yield would often max out at between 1.5 and 2 million cells, regardless of cell line or what kind of cells you were differentiating to. And when it comes to stem cells grown from PSC aggregates and differentiated as spherical aggregates, there's really only 3 limitations. There's the aggregate size itself. Once it becomes too large, you'll have diffusion limitations throughout the aggregate. But other than that, it's nutrients and oxygen. So if you're continuously supplying nutrients and you get a plateau in your cells, it's because they don't have enough oxygen. And when you do that in the incubator, it's all about free-flowing headspace. So the headspace to volume ratio is what dictates how much oxygen is available in a non-controlled environment. So here you see when we control our oxygen, we can increase the cell yield in the MiniPRO system. But it's not just about increasing cell yield, it's about providing a controlled, better environment for your cells. So when you do anything in the incubator, T-flasks, bioreactor, G-Rex, it's an uncontrolled gassing environment. So when you seed your cells into that bioreactor, it's at what we call 100% dissolved oxygen relative to air. So basically 21% oxygen, that's what you seed the cells into. And they say, wow, we have all this oxygen, and they establish their oxygen consumption rate. And they start eating the oxygen, and as they grow more and more, the oxygen levels in the media go down. And then you feed it, and the oxygen spikes up, and then it goes down again, and it spikes up, and it goes down until you have too many cells that as soon as you feed it, it goes right back down to zero, and it can't produce any more cell expansions, and it plateaus off. That's not a very controlled environment. With the MiniPRO, you start controlling it at your chosen dissolved oxygen concentration right from day zero. So in this case, we controlled it at 50% dissolved oxygen relative to air. So that's a hypoxic environment at about 10%. And it controls consistently throughout its 7-day culture. This is the oxygen input graph. And what it shows you is in the first 4 days, it's controlling at 50% dissolved oxygen, but the system isn't asking for extra oxygen to be put into the airspace. It starts to ask for it about on day 4, and that demand or that ask for oxygen into the headspace to maintain 50% control increases as the amount of cells increase. So not only are we able to increase the yield, but just maintain better control. Here again, it's just showing that we've maintained that very important original scale-up variable of hydrodynamic throughout our PBS 0.5 into the MiniPRO conditions, so we can maintain what I call process attributes. And one of the most important process attributes in pluripotent stem cell expansion is the aggregate size and the aggregate size distribution. So we want to maintain narrow size distributions with one kind of peak around your aggregate average. And that's what we see in both our PBS 0.5 system and in our MiniPRO system. Along the bottom is just demonstrating that this MiniPRO works in both a reproducible, so testing it over multiple experiments, and robust way. And by robust, I mean it works throughout a variety of process input variables. So in the upper portion of this graph, we're working with a more traditional seed train, where we take a cell vial with a couple million cells, seed it into 2D for multiple expansions before going into our 3D culture. In our graph along the bottom, we've generated this using a new seed train where we take a high density cell bank, which was adapted to shear by being cultured in a bioreactor prior to that. And it's frozen down at 100 million cells in a vial. And we thaw these directly into our bioreactor culture to shorten this expansion phase and go right into bioreactor culture intended for differentiation cultures. We also have tested our process with multiple different expansion media, both M-teaser as well as a modified B8 media, which is a derivative of E8 media. And you see the story stays the same. In the PBS 0.5, which is in the incubator without oxygen control, there'll be consistent growth that plateaus at around 1.5, 2 million cells per mil. Whereas you can extend this growth, in this case, we extended up to about 3.5 million cells per mil by adding oxygen and control in the MiniPRO system. These cells do maintain characteristic pluripotency markers. Here we just stained for SOX2 and OCT4. So that's the story of our MiniPRO enhancement compared to the PBS 0.5 system. Now here we're demonstrating that it is a true scale down model to our 3-liter plus systems. And when I define scale down, I'm looking for something that is linearly scalable, which means we can maintain those growth rates, that cell per mil concentration that we achieve in our optimized scale down MiniPRO in these larger bioreactor systems. So in this case, we're comparing our MiniPRO to our PBS 3-liter. The scale-up correlation that I use is maintaining a volume average energy dissipation rate. This is determined through computational fluid dynamic modeling and has been very proven in literature to be one of the dominating factors in controlling our aggregate size and aggregate size distribution. So given that that is one of my main process attributes, that's what we use as our scale-up correlation. And it tells us that if we've optimized our MiniPRO to run at 40 RPM, we should run our PBS 3-liter at 27 RPM to maintain these characteristics and scale up. So here we see, yes, we have maintained our growth kinetics when operated under the same dissolved oxygen, pH, and feeding regimens. What we see here are a variety of other process attributes that are all used to validate these cell counts. So cell count is just one output. We want to look for other evidence that they are behaving similarly. So in this case, we're comparing their cumulative growth rates and their doubling populations, which comes from our cell kinetics. But here we're looking at the online pH readings between the MiniPRO in orange and the PBS3 in gray. You see that they overlap, as well as their metabolite consumption rates of glucose and glutamine and production of lactate and ammonia. And then again, very importantly, we see that between the MiniPRO and the PBS3 leader, right from day one, these are seeded as single cells. They form morphologically healthy aggregates that grow in size as the cell expands throughout the 7-day culture period. And both the average size maintains very similar between the MiniPRO and the PBS3 leader, as well as the distribution. So the height of those boxes are tight and narrow, meaning that the average aggregate sizes are all quite similar. We have no bimodal peaks or two different populations there. And that continues throughout our day 3, day 6, and day 7 analysis. So that is my presentation on the MiniPRO.